What? Current event? Oh, I have no idea. What happened today, mathematically speaking? I don't know either. I don't Google Math News either. I actually read an article. I think it was on Saturday or something over the weekend that they did a study about some of those beautiful mathematical equations, and apparently they studied the brain's reaction to them, and apparently it's equivalent to just looking at the beautiful painting and the sunset. And then there are some of those equations that apparently trigger same responses in your brain. Yeah, just looking at the equations. Oh, well, that's clearly. I had actually I don't know, but like the pretty one, the e to the I pi plus one, that one. That apparently that's just it's like looking at the painting. That does not does not make you feel good inside and warm when I write this on the board. That thing. That's beautiful, right? When you look at it, it's like I want to put it on my wall and look at it. Doesn't that make you warm? No, it's supposed to make you happy. This is good. This is nothing. It's just actually I'll teach you. We'll do this. We'll prove why that's the case, just for the fun of it. But that's supposed to make you feel good, just like a painting. Well, no, it's not really current, but I've read it over. Apparently, there's a statistical proof that that's pretty. If that makes sense. That's pretty. Come on. Okay. I want to do a few more examples of that improper stuff. Actually, I only have two examples. Here's an example, an integral from 0 to infinity, dx over square root of x, x plus 1. So there are two problems. Improper. There are two problems with this integral. First of all, 0 is not a good number, right? 0 itself causes trouble. The function is not continuous at 0. And so is, the infinity. That's another issue. So we need to fix both of these. Okay? So the way we're going to do this, we'll split this integral into two. We're just going to grab a number from 0 to infinity, any number that you like, 1, and I'm going to make this into two problems. I will take a limit as t approaches 0 from the right and integrate from t to 1 of this function. And then, well, let's use a different letter just to be more precise. Let's take, I don't know, b approaches infinity from 1 to b. Because this problem combines two types of improper integrals. Type 1 when you have infinity, and type 2 when you have a discontinuity. Now, I'll integrate this thing on the side. I actually want to find the antiderivative so I don't have to mess with, substitution and resubstitution. But if you just want to do the antiderivative here, one thing that we can do, we can substitute the relation between x and the square root of x is that if you square the square root, you get x, right? So this looks like, I can think of this as my u squared plus 1 situation. And then if I let u equal the square root of x, the remaining square root of x will actually go away as a part of the du, because du is 1 over 2 square roots of x dx, which makes dx to be 2 square roots of x du. And if we substitute, I'll just keep in mind that I'm going to cancel this square root. So this is 2 square roots of x du over square root of x, and then x plus 1 becomes u squared plus 1. So these two cancel. Is that okay? And the antiderivative of 1 over u squared plus 1 is the arctangent. So this becomes 2 arctangents of u plus c. So technically that's 2 arctangents of square root of x plus c. Is that okay? Well, I mean, b goes to infinity, t goes to 0. They're limiting, right? Those are limits. So yes. But now, the first one is just the limit as t goes to 0 from the right of this function to inverse tangents of square root of x evaluated from t to 1. And the other one would be the limit as b goes, I mean, you can use t in both cases. Those are separate limits, but it's just, your book uses different letters just not to confuse it, but I don't see why. So what were we doing? Oh yeah, so that's 2 inverse tangent of square root of x evaluated from 1 to t. Yeah, b, thank you. See, that makes it more confusing. And I'm not pulling 2 out yet, because I have to be careful. I don't know whether those limits exist, and I can only pull the 2 if limit exists. But anyway, so if I do the math, so this is the limit as t goes to 0 from the right, and that becomes 2 inverse tangent of square root of 1 minus 2 inverse tangent of square root of t plus the other side, which is a limit as b goes to infinity, and this is 2 inverse tangents of square root of b minus 2 inverse tangents square root of 1. Is that okay? So what happens, I mean, this is a constant, and what happens with the inverse tangent as t goes to 0? So basically, what's the inverse tangent of 0? 0, so right? So that goes to 0. So I'm not even going to compute, I mean, I can compute the inverse tangent of 1, that's not hard. But it will most likely cancel with that one, right? Do you see that? They have opposite signs. So I'm just going to write it as it is. 2 inverse tangent of 1 plus, what about this limit? So as b goes to infinity, square root of b goes to infinity, and then we talked about it last time. What happens to the inverse tangent? Pi over 2, so that's plus 2 times pi over 2 minus 2 inverse tangents of 1. So these two cancels, and you're just left with a pi. And the reason why we didn't just cancel them right away or didn't do any simplification, because we have to be very careful. I cannot use limit laws when I don't know whether those limits exist. Right? But after I took the limits, I got some numbers, so then we can start using the limit laws and cancel things. Does that make sense? I just have to be a little careful here. So that's it. So any questions? So this thing combined two problem areas. One, we had infinity as one of the limits of integration, and the other limit of integration was actually point of discontinuity. Right? We cannot have zero, so we have to take it into two pieces. So combine two improper situations in one. How's that? Have any questions? Yeah? No? Okay. Hmm? Well, yeah. That's a pretty answer. We were just talking about the pretty, right? Yeah, the rest of it is, yeah, clearly. Anyways, here's another problem. We haven't done this in a while. So let's take this curve for x is greater than or equal to 1. So it's and let's rotate around the x-axis. We haven't done that in a while. So if you rotate, you get what? Yeah, like that. I don't know what it is. Sure. And it just keeps going to infinity. I want to find the volume of that shape. Hmm? Oh, I don't know. Because that's, so you rotate around the x-axis, we can use the disk method, right? So the volume would be the integral, well, from 1 to infinity, and then it's pi r squared. So the radius of each one of those is the value of the function, so it's times 1 over x squared dx, right? Well, based on what we did on Friday, that should converge. Remember we did that the p thing? If the power is greater than 1, it will converge. So we can actually, if we know that beforehand, I can pull the pi out. I know it's a convergent integral. And then I'll write it as a limit as t goes to infinity from 1 to t 1 over x squared dx. And we did that one. We did this problem on Friday. Do we know the result? Now I'll just compute it. What? Like 1? Yeah, if you just do 1 over x, then it's infinite. But if you do 1 over x squared, it was something else. It was like a third, wasn't it? I don't remember. Let's just compute it. It's not that hard. So the antiderivative is negative 1 over x, right? So it's a pi times the limit as t goes to infinity of negative 1 over x, evaluated from 1 to t. So what is this? It's pi times limit as t goes to infinity of negative 1 over t plus 1. Also, it's 1, right? So 1 over t goes to 0. 1 is 1, so you just get another pi. Isn't that beautiful? What? Well, it approaches 3.14. That's what we need to realize. It doesn't quite equal. That's the thing that we need to, this is the tricky part, because this is a limit. right? That means I can get as close as I want to pi. I never quite get to pi, and I'll never definitely go above pi. But that's the limiting value, right? Yeah, because in the next chapter we'll be doing things like adding bunch of fractions, 1/2 plus 1/4, and adding bunch of rational numbers, and the answers will come out like some version of pi. So you should question it, like, well, how on earth can I add rational numbers and end up with irrational numbers? Rationals are closed under addition. I shouldn't be getting sum of fractions equal something that's not a fraction. But again, this is not the equal sign per se is 2 plus 3 equals 5. That's a limit, right? It's still going to be some rational number, but it's as close as you want to some weird irrational. So that's what we need to know. This is all the integrals are limits as well, right? And we define them as limits. So anyway, so that's it. But the math makes sense. The philosophical issues we're all going to have those. But as far as the math, the way we define things, it seems to work out, right? Okay, well, good. Any other questions? Okay, well, that's chapter 8. Let me pause this. That was a big lecture.